Hello again. We're going to continue with our look at alternating infinite series. So the first time around, we just talked about how to check for convergence with the alternating series test, where an alternating series converged if the terms of that series, again, the part that's not causing the alternating sign, so if the magnitude of the terms of the series headed to zero and the terms were monotonically decreasing eventually. So if there came a moment where from that term on the terms were monotonically decreasing, then with those two conditions met, we would be safe to say that that alternating infinite series converged. So we're going to move on to part two today, where we take a look at what's called absolute and conditional convergence. Quite a handy topic that can actually save us quite a bit of time depending on the infinite series. So kind of right out of the gate, the main thing is right here at the top. So if the series, again, infinite series, sigma absolute value of a sub n converges, then the infinite series without the absolute value also converges. So what this is saying is, again, this is offered without proof. Anybody that would like to see the proof of this is always welcome to come in and we can go through that. But offered without proof is this, that if you have an infinite series that has negative terms and you put absolute value on the terms of the sequence that makes up the series, basically eliminating all the negatives, if the resulting infinite series converges, then the one that had the negative terms also converges. So its usefulness, as I see it, it's probably got lots of uses, but for us in the short term is if you have an alternating series and you're looking at it and you're thinking, the alternating series test might be a little tricky, you could gamble a little and you can say, well, let me put absolute value on the terms of that infinite series and turn all the terms positive. And if I can prove that converges, then I know for certain the alternating series I started with converges. So for us in the short term, its usefulness will be we can sometimes, as you'll see, we can sometimes avoid the alternating series test by putting absolute value on the terms of our series and showing that that one converges. Therefore, the one with negative terms would also converge. So we got a couple definitions here that are important. So the infinite series with nth term a sub n is absolutely convergent if that same infinite series whose terms are all positive converges. And then an infinite series whose terms are given by a sub n is conditionally convergent if the infinite series with the negative terms converges, but that same infinite series with all positive terms diverges. And the name comes from the fact that basically what it's saying is there needs to be this condition that some of the terms are negative for it to converge, and without that condition it diverges. So if you look at that again and stop and think about it, see if that makes sense to you. So we have an infinite series and we say it's conditionally convergent if when we use its negative terms we get a convergent infinite series, but the moment we switch all those terms to positive, it diverges. In other words, it only converges with the condition that some of the terms are negative. The other one is basically saying, look, if all the terms are positive, it converges. If any of the terms are negative, it converges. So it just absolutely converges. It's absolutely convergent. It doesn't matter whether some of the terms are negative or positive. Either version converges. And again, the usefulness to us is going to be, you have a alternating series and you're like, oh man, that one's going to be tough to do the alternating series test. I'm going to gamble a little. And what if all the terms were positive? Can I show that converges? If I can, then boom, the alternating version also converges. We kind of get that one for free according to the theorem. All right, so we've seen some examples of these. So let's kind of revisit some of the things we've done and see that we've actually kind of seen this before. So it says, give an example of a conditionally convergent series and explain. So the classic example is the harmonic. So we showed earlier that the alternating harmonic, right? So this is the alternating harmonic series. We showed that converges. So the alternating harmonic series, this series converges. The one that alternates converges. So if we apply the alternating series test, we can prove that it converges. Or, again, if you don't trust that, like I requested, use some software. Have it kick out some partial sums and convince yourself that, man, those partial sums really do head towards a bound. So the harmonic series, if it alternates, converges. However, if you slap absolute value on that, which turns it into the harmonic series, not the alternating one because nothing's negative now, it turns it into the harmonic series. And this series diverges. So this is a conditionally convergent series. So it only converges on the condition that the terms alternate. So I'll use a different color just for emphasis here. So -1 to the n times 1 over n, again, that's the alternating harmonic, is conditionally convergent since it only converges with the condition that it alternates. I mean, that's where the name comes from. We need that condition of alternating for it to converge. All right, what about an absolutely convergent series? There's plenty of those too. So for example, let's say we had 1 to infinity of -1 to the n over n squared. So this converges. Well, why don't we go ahead and show the usefulness of being absolutely convergent? Why don't we do it that way? So let's say you came across this alternating infinite series in the wild and you're like, oh man, I got to figure out if this thing converges or not. And let's say you're staring at it and you're like, man, I don't know, the alternating series test might be kind of tricky. I don't know if I want to go through that. Well, again, you can gamble. You can gamble. You can say, all right, All right, wait a minute. There was that theorem that said if all the terms were positive and that series converged, then the alternating one, or the one that has negative terms, will also converge. So maybe you gamble. Okay, so let's gamble. So our gamble is if I slap absolute value on this, which all that would do is eliminate any negative numbers, so it would turn into this. All right, so if I put absolute value on the terms of the sequence that makes up or comprises the series, it turns it into a p-series. So this is a convergent p-series. P equals 2, and if p is greater than 1, the series converges. So our gamble pays off, because remember, the theorem at the beginning of today said if the infinite series, when you make all its terms positive, converges, then the original one with negative terms converges. That's what we started with. It's right back up here. So right here. So if the series with positive terms converges, then the series that had some negative terms also converges. So I get to use that theorem now and conclude the original one I started with converges. So therefore, 1 to infinity, negative 1 to the n over n squared converges, and some weird handwriting there, and we have shown that that infinite series is absolutely convergent. Now, I said let's gamble, because it is a gamble. You might get an infinite series. You might get an infinite series with negative terms, probably alternating. That's typically, if we have negative terms, that's usually what we're dealing with at this level. And you might get an infinite series that's got some negative terms. You're like, all right, man, I'm just gonna make all the terms positive and hope that converges. But it might not. It might not. So then your gamble didn't pay off. So you make all the terms positive, you find out that that one diverges. Ugh. All right, now you have to go back to the original and apply the alternating series test. Or if it's not alternating, it's just got some weird negative numbers somewhere, you got to try something else, but that's not going to happen on the AP exam. So at that point, it was probably alternating to begin with, so you're going to have to go back to the original series and apply the alternating series test anyway to determine if that given series converges. So it is a gamble, but I mean, with practice, it becomes less of a gamble, because with practice, you'll kind of be able to, you'll start to be able to look at infinite series and go, all right, it's alternating, but if it wasn't, I know that converges. All right, so that's how I'm going to prove the alternating one converges. So I'm going to slap absolute value on it, show that that converges, and then I know the original one does. So it's less of a gamble the more practice you get. All right, so with this in mind, let's look at some more alternating series. All right, so determine if the following converge or diverge, and then classify any convergent series as absolute or conditional. All right, so in case that wasn't clear before, we only care about the classification of absolute or conditional if the series converges either with the negatives or without. If the whole series just diverges, no matter what kind of terms it has, positive or negative, then this whole idea of a convergent series being absolute or conditional, it doesn't apply, because it doesn't converge no matter what. All right, so let's take a look at this first one. It definitely alternates, right? We can see that right here. Negative 1 to the n is going to cause this to alternate. So We could gamble. We could gamble. We could slap absolute value on it. Um, but but the top is n factorial and the bottom is 2 to the n. Both of those increase rapidly, but man, factorial increases just so much more rapidly. So I think the numerator, as n gets larger, I think the numerator is pretty much just going to way outpace the denominator. So I think these terms, I think the terms of this series, basically the terms that make up the series, the sequence that makes up the series, I think the terms are getting larger. So I don't think I would start by assuming it converges. I think I would take, I think I'd take the path where I think this thing diverges. So let's check. Um, so the limit as n goes to infinity of n factorial over 2 to the n, well, we don't know how to do the derivative of n factorial, but I don't know that we need to. So yes, I agree, this is infinity over infinity, and we could apply L'Hopital's rule, but we don't know the derivative of n factorial. That's not something we've studied. But I don't know that we need to. I don't think it takes a complex analytical argument to convince somebody that n factorial, that value grows very quickly. And yes, 2 to the n also grows quickly, but man, n factorial grows a lot larger. So this expression is just headed off to infinity. This limit doesn't exist. Right? This limit does not exist. So that's a weird why, by the nth term test, this series diverges. So it is neither absolutely nor NOR, man, my handwriting, what's going on? Is neither absolutely nor conditionally convergent. I mean, that idea doesn't even come up because this infinite series is not convergent at all. I don't care if it's alternating or not alternating. Those terms get giant. So this infinite series has no chance to converge. So that's why that's the first example is like, don't, now that we've learned this idea of absolute and conditional convergence, don't look at an infinite series and think, well, it's got to be one of those. No, it doesn't. No, it doesn't. It could just be an infinite series that if you turn the machine on and it starts cranking out terms and adding them up, that sum heads off to either positive infinity or that sum heads off to negative infinity, meaning it's an unbounded sum. It just grows as large and large as you can imagine, either in the positive or negative direction. Let's take a look at another one. So let's do this one right here. Negative 1 to the n over the principal square root of n. Now this one at least has a chance to converge, right? Because the terms are headed to 0. The terms are headed to 0, right? So, if you do the limit as n goes to infinity, 1 over principal square root of n, that's headed to 0. All right, so might converge. All right, so there's a chance. There's a chance. Question is it absolutely convergent or does it require that alternating? Does it require the alternating? Well, maybe you gamble. Maybe you gamble, right? So let's gamble. You're just a gambler. You're like, oh man, I love letting it ride. So if I slap absolute value on that, so boom, I put absolute value on it. Well, that just turns it into a p-series. But that diverges. So this diverges. P equals a half, and any p-value between 0 and 1, including 1, implies divergence. So And you might have recognized that already. And that's the idea. The idea is that it's not really a gamble if you've been diligently working on these convergence divergence tests, you've started to get a feel for which infinite series are going to converge and diverge. So we gambled and we lost. So without the alternating, it diverges. So now we're back to square one. I have to apply the alternating series test. I mean, I have no choice. So alternating series test. Here we go. We've already done the first part. Yep. Terms head to zero. Terms head to zero. Now we just need to show the terms. We just need to show that the terms decrease. And you have a couple options. You can do a derivative. I don't mind an arithmetic argument as long as the arithmetic argument is convincing and makes sense to people other than yourself. So in this case, an arithmetic argument would probably work without a lot of effort. So the nth term is that, and the n plus first term, so the term after that, is this one. Okay. Well, as long as you're doing greater than or equal to 1, so for n greater than or equal to 1, n plus 1, the principal square root of n plus 1 will always be bigger than the square root of n, right? Don't believe me? Pause the video, start plugging in positive integers for n, and let me know once you're convinced. So since that's true, that implies that 1 over the principal square root of n will always be less than 1 over the principal square root of n for n greater than or equal to 1. Right? So if you plug in 1 over the square root of 2 is less than 1 over the square root of 1. Again, if you don't believe me, try it. Get out your calculator. Check the arithmetic. Therefore, the given alternating series converges. But remember, if its terms were positive, it diverged. If its terms were positive, it diverged. In other words, the given infinite series is conditionally convergent. It only converges with the condition that it alternates. So this one is conditionally. That's a weird Y. Convergent. So conditionally convergent. So the given infinite series converges simply because it's alternating. The moment you get rid of the alternating, nope, it diverges. All right, let's take another one. Okay, we got this bad boy. And even though that exponent is gnarly, not real sure why the author, I think they just kind of wanted to flex a little bit. But this is what makes it alternate. Again, you can pause the video, plug in some values of n, and see that that's what's causing it to alternate. So, again, you might be able to eyeball this and figure out that the nth term test for divergence is going to show that it might converge. So if I do 1 over 3 to the n, that definitely heads to 0. So convergence is a possibility. Now maybe after the last example you're a little timid. You're like, man, I don't want to gamble anymore. I just keep losing my money. But I would say don't give up that easily. So let's gamble. Let's gamble. So if I throw absolute value on this, basically if I get rid of the alternating, so I throw absolute value on this thing here, it turns it in to a geometric series. So I just end up with 1 over 3 to the n, which is geometric. R is 1/3. Absolute value of 1/3 is less than 1. Therefore, the series converges. Oh man, our gamble paid off. So, since the infinite series, when its terms are all positive, converges, the theorem says that the one that has negative terms will converge. We're done. I don't have to apply the alternating series test. So therefore, the given alternating series is absolutely convergent. So our gamble paid off. Because look, I think we'd all agree, convincing someone that a geometric series converges by looking at the common ratio is way easier than doing the alternating series test. So, in my opinion, this was the better way to do this, is to go ahead and gamble. Notice that all positive terms would be a geometric series with r equal to 1/3, so we can pretty quickly show convergence. Therefore, the given alternating one converges. All right, let's take a look at one more. All right, we got another alternating series. Here it is, right there. There's the part that makes it alternate. Right off the bat, you should be kind of paying attention to the terms here. Notice, ignoring the alternating part, notice this. Notice that the denominator is the natural log of n plus 1. But man, look, we've all had Algebra 2. We've all had pre-cal. The natural log function, it increases slowly. Right? The natural log function, I know this is natural log of n plus 1, but come on, that's really not that different than the natural log of just x or n. N plus 1 just means shift at left 1. So the natural log function increases really slowly. So since this increases slowly, relatively slowly, then 1 over that is going to decrease slowly. So these terms are not getting really small really fast. So hopefully by now you've started to get an eye for infinite series that are likely to diverge. Look, nothing's guaranteed until you prove it, but you know, my hope is you're starting to get an eye for like, oh man, I bet that diverges. That's kind of what I'm going to start with. So with that in mind, since I think that all positive terms will cause this to diverge, I don't think I would gamble. Now you could. I'm not going to say don't gamble, but I'm not going to. So my gut is that if these were all positive terms, this thing's going to diverge. So I think I would just be like, look, I'm going to do the alternating series test. So the limit as n goes to infinity of 1 over a natural log of n plus 1 does head to 0. So all right. Next, the nth term is 1 over natural log of n plus 1. The n plus 1 term, so the next term after the nth term, would be natural log of n plus 1 plus 1, which is 1 over natural log of n plus 2. And again, I think you can do an arithmetic argument here. I mean, it's not going to be too hard to follow. The natural log of n plus 2 should be bigger than the natural log of n plus 1 for n greater than or equal to 1, right? So the natural log of 3 is bigger than the natural log of 2. I think that's true, right? So the natural log function looks like. Therefore, 1 over the natural log of n plus 2 would always be smaller than 1 over the natural log of n plus 1. In other words, the terms will be decreasing. I mean, again, what we're proving here is that the terms of this series are getting smaller. They're monotonically decreasing. And again, even if it's not true for 1, it's going to be true eventually. Like once you get past, I don't know what, e, so I guess 3, right? So e is 2.7 something. So, but n is a positive integer. So even maybe it's only true for n greater than or equal to 3. Okay, that's fine as long as from 3 on the terms are always smaller. They're monotonically decreasing. So by the alternating series test, we have now shown that the given alternating series, let me make sure I got it right, converges. So it's at least conditionally convergent. I've just shown that if it alternates, it'll converge. So it's conditionally convergent. Now, remember, I was gambling. I was thinking that if I put absolute value on it, it's going to diverge. Now, I could be wrong. But we now need to go check it, right? I'm supposed to figure out if this is absolutely convergent. So I need to go see if it'll converge when all the terms are positive. So step 3 would be to check if it is absolutely, that's a weird B, absolutely convergent. Okay, well, all right, here we go. So if I slap absolute value, it turns it into this infinite series, just 1 over natural log of n plus 1. So I need to now check if I need to apply a convergence divergence test to see if it's, which one it is. Again, my guts tell me diverge, so let's see what happens. I think I can do a direct comparison test. I think. Let's try it. Let's compare to our favorite divergent series, 1 over n, the harmonic. So diverges p equals 1, and any p-value between 0 and 1 equal to 1 implies divergence. Okay. So what if I compare it to the harmonic series? So I'm going to compare it to the infinite series 1 over n. Now for the direct comparison test to work, I need to show that my terms of the series I have are bigger than the terms of the harmonic. And again, I think this is relatively easy to do. If you need to use a calculator, you can. But if you go look at the terms of 1 over n, they are smaller than 1 over natural log of n plus 1. The first so many terms are not. But once you get about to the 10th, 11th, 12th, 13th, 14th terms, you can go see that the terms of 1 over natural log of n plus 1 are smaller, or I'm sorry, are larger than 1 over n. So if it's not alternating, it diverges. We could do the integral test, I think. Maybe not. Do we know the antiderivative of 1 over natural log of n plus 1? We might not. So maybe the integral test would be not a good choice there. I'd have to give that a whirl. But the direct comparison test works. Using your calculator to check which terms are bigger, that's fine. We can lean on that a little bit. We have it available. So kind of the main point of today's video is just that we can gamble a little. We can look at an infinite series that has negative terms, and if we look at it and we think, oh man, if those terms were all positive, I could show it converges. Well, if that's true, go ahead and do that, because if you show that converges, then the one that has negative terms also converges, and your gamble will pay off.